The left side of the screen is incredibly stuttery and it's trying to run the game on 8 gigabytes of VRAM. The right hand side of the screen is running a lot more smoothly on a 16 gigabyte graphics card. And now these are basically the same graphics card. They're both 4060 Ti's, so their performance will be the same unless you run over the 8 gigabyte VRAM buffer. So in this video, we're looking at how big of a deal is, how bad is 8 gigabytes of VRAM in 2024. We'll be looking at a lot of the newest games from 2024, some of the later games from 2023, and this can be affected by a lot of different things. It can be affected by the resolution you're running at, the graphic settings you're trying to use. Are you using upscaling? Are you using frame generation? So we're gonna look at all of those things in today's video, but you can tell that it absolutely can cause a crazy performance difference. Here we can see that the 16 gigabyte card is 4 times the frame rate at 8 versus 32 average, and more than 4 times the frame rate in the 1% lows. It's the lowest 1% of frames at 6 versus 28. Pretty crazy differences. So if by the end of this video you're feeling like your 8 gigabyte graphics card should probably get sold to someone else, Jawa.gg can take that graphics card off your hands to help you fund your upgrade by offering you the simplest and fastest way to sell your GPU, and huge thanks to them for sponsoring today's video. Also, you could look for your next GPU by searching their listings, and I can get you $10 off your first purchase if you use code OWEN10 when you follow the link in the video description and or the pinned comment. Now, I know a lot of people, when they upgrade their graphics card, they toss the old one in the closet. It's not doing anything for you to help you fund your upgrade. Again, that's where Jawa can help out by totally taking the hassle out of that. You click the Get an Instant Offer button, and it's as simple as this. You tell them the GPU model and condition, and they give you an instant offer. You print the free shipping label and mail them the GPU because all the shipping costs are factored into the offer that they've given you. They inspect the part to make sure everything checks out, and most sellers get paid within 1 business day after the part is received. So it's totally simple and easy. And again, if you take a look at their other listings to find your next GPU, use code OWEN10 to get $10 off that first purchase. Now, let's go ahead and take a look again at a wider variety of graphics settings and see what's really going on here. However, I do want to point out one more thing, which is how do we spot this is for sure a VRAM difference? Well, let's look at this stat counters up here. Well, first of all, I mean, if the frame rates are this different and the only difference between the two GPUs is their VRAM amount, which is the case here other than the cooler model, which could at most account for maybe a 1 or 2% difference in scenes and then run-to-run variance of 1 or 2%. But if we're seeing 4 times the frame rate, it's definitely a VRAM issue. But let's also look at the stat counters up here. The green memory line is the GPU's reported per process, VRAM allocation, and then per process usage. And you can see here that both of those numbers are above 8 gigabytes, whereas the card with only 8 gigabytes doesn't report more than 8 gigabytes because it can't, it doesn't have it. So what happens when a game goes over its VRAM buffer? Well, it still tries to access the information. So where does it have to go? It has to go to system memory rather than the memory built onto the GPU. And that takes longer. That's a slower process, so the GPU has to wait, and that slows down the overall frame rate. Sometimes it can cause stutters. If it doesn't get access to information in time, it can cause missing textures and other graphical corruption issues, and some games will occasionally just crash. Now, we can see the reported system memory here in blue, and again, it shows the allocation versus per process usage. And especially if you look at that per process usage number here, which is about 6 gigabytes on the 16 gigabyte card, you can see it closer to 8 gigabytes, meaning about 2 gigabytes higher on our 8 gigabyte card, indicating, as we see, that if you don't have room to put the information in VRAM, it has to go into system memory, and therefore that's a slower process, and in this case, it's absolutely crippling. Now, it's not always this extreme. So for example, if you use DLSS, here I've kicked it on at the performance mode, which is a 1080p internal resolution, but then upscaled using the DLSS algorithm to try to issue a 4K-like output resolution. you can see that the performance numbers are a lot better on both cards, and the gap has closed significantly, but it's still a significant gap. If we stop for a second to look down at my performance numbers here, we see the 16 gigabyte card is 77% faster at 69 FPS average, nice, versus 39 on the 8 gigabyte card, and the 1% lows, the lowest 1% of frames, is an 82% advantage at 62 versus 34. So pretty big differences there. While rendering at a lower internal resolution helped, it was not enough to overcome the pretty significant performance gap here. Now, another thing you could do is turn down settings. Here I went down to high settings rather than very high, and I also used DLSS quality. Now here we can see that the performance difference is only 2%. So I chalk that up to run-to-run variance or a difference in the cooler models between the two GPUs. So this is not showing a VRAM issue. So we're showing that both GPUs can run the game fine at these settings. So we found settings where it worked, but we also found some settings where the 16 gigabyte card could have worked, but that didn't. However, what if you wanted to kick on frame generation? So if I say FG here, it means I've kicked on DLSS 3 frame generation, and now we're seeing the 16 gigabyte card 41% faster and 2.52 times faster in the 1% lows. And actually, if you take a look at it, you'll see a very spiky frame time graph on the 8 gigabyte card. And actually, if you look at the numbers, the 8 gigabyte card is performing slower. Let's actually go back for a second. Frame generation numbers versus when I didn't have frame generation on, the 8 gigabyte card was faster with frame generation off than it was with frame generation on. What's going on with that? Well, frame generation uses VRAM. So if you're already right at your card's VRAM borderline and then you kick on frame generation, performance can plummet and you can get these spiky frame time graphs with stuttering. So that's another thing we need to be taking a look at as we test settings. Now, what if we go down to 1440p resolution? Well, 1440p very high settings seem to be running okay here. We're tied at 58 FPS average on both GPUs, so it doesn't seem to be an issue in my test sequence here. However, I've heard other people tell me that on their 8 gigabyte cards, they do eventually run into problems in this game in certain scenes, but I can only test so much if I'm going to be testing all these games for this video. However, I did notice that if I kick on DLSS quality plus frame generation, which a lot of NVIDIA users would want to do, I actually get better performance on the 16 gigabyte card, again, likely due to frame generation using more VRAM. So we get a better frame generation experience on the 16 gigabyte card than we do on the 8 gigabyte card, which is, again, kind of unfortunate when that's one of the big parts of the NVIDIA feature set. If we go down to 1080p resolution at very high settings, both GPUs are performing basically identically here. 84 FPS average, 1% lows at 74 and 73. Again, if we're talking single-digit performance differences, it's most likely either run-to-run variance or differences in the GPU cooler models or both. So this we would say is a tie, and there's no VRAM issues at 1080p max settings. Now, what if we go to Horizon Forbidden West at 4K very high settings, so max settings and resolution here, we can definitely see problems for the 8 gigabyte card, with the 16 gigabyte card 21% faster in the averages and 58% better in the 1% lows, with some spikes in the frame time graphs showing up on the 8 gigabyte card. Now, we could try to rein this in by changing graphics settings, maybe using DLSS. So if we kick on DLSS performance mode, which again is a 1080p internal resolution, but then trying to output a 4K-like image, I restarted the game several times to be sure that this was correct, but the 16 gigabyte card basically doubles its performance. The 8 gigabyte card can't, due to the fact, now its power usage is really low here, if you take a look at that. So what's going on here seems to be that it just can't utilize the more performance due to running into the VRAM issues. The VRAM was still holding it back. So yeah, huge differences there. At 4K high settings, the differences are less profound when they're both kind of struggling here. But it is a 39% advantage in the 1% lows for the 16 gigabyte card and a 9% advantage in the averages. And I did, again, try turning on DLSS, this time at the performance mode, and once again, I do restart the game in between changing graphic settings to make sure they're applying properly, and this is what I'm seeing here. Again, we're seeing the 16 gigabyte card able to stretch its legs up to 63 FPS average, but the 8 gigabyte card didn't. Again, it must be being held back by trying to reach into system memory. And you do see that system memory is a much higher usage here on the 8 gigabyte card. I did try going down to medium settings with DLSS performance, and then the 8 gigabyte card was finally performing well, although it's actually still slower than the 16 gigabyte card by 4% in the averages and 13% in the 1% lows. Unfortunately, it sounds like my heater just kicked on a little bit in the background, so you get a little more background noise on the microphone here. At 1440p resolution, at very high settings, we're once again seeing VRAM issues for the 8 gigabyte card. Again, I'm restarting the game between all of these tests. This is just how it's going. So we're at a 13% advantage in the averages, but a 42% advantage in the 1% lows, with a lot more spikes on the frame time graph for the 8 gigabyte card here. If we go ahead and kick on DLSS quality, the performance goes up on both graphics cards, but again, especially in the 1% lows, the issues have not been completely solved for the 8 gigabyte graphics card, with a 62% advantage for the 16 gigabyte card at 68 versus 42, and a 19% advantage in the averages at 80 versus 67. So again, while it's not a miserable experience on the 8 gigabyte card, it certainly makes some differences. If I go down to high settings but leave it at native resolution, our numbers finally kind of balance out here, with not too big of a difference in the 1% lows at 55 versus 52. That could just be run-to-run variance. And the averages are tied at 63. So 1440p high settings, everything's fine. But this is a 1440p game where you're having to turn down settings in order to get a good experience. I also tried kicking on DLSS quality, and this did seem to boost frame rates up over 80 on both GPUs. We're within 1% performance of each other, so not a lot to see here. I think I'll actually skip ahead a little bit. At 1080p resolution, though, I was actually seeing some differences here in performance. So then I went ahead and kicked on, sorry, I think this is the high settings here rather than very high. I'll block that with my face. And that did get everything to balance out and perform pretty well here. But yeah, we're definitely seeing Horizon Forbidden West wants you to have more than 8 gigabyte of VRAM to play comfortably on the very high settings in the game. Now let's move on to one of the biggest visual showcases of the year, and this is an Unreal Engine 5 game, really taking advantage of all the Unreal Engine 5 feature set, pushing everything to their limits, with Hellblade 2: Senua's Saga. This game is in a letterboxed resolution, unless you mod it, so I'm testing it at its default settings here, and we can see that at 4K high settings, and high is the highest setting here, the 8 gigabyte card is absolutely crippled. Neither GPU was doing great, though. So by kicking on DLSS performance mode, but keeping the high settings, the VRAM is no longer a problem. The GPUs are now basically tied within 1 FPS of each other in the 1% lows and tied in the averages. However, neither GPU's, crushing it in this game. It's still incredibly demanding, but we're at least not seeing VRAM issues once we've kicked on DLSS performance mode. I tried going down to medium settings with DLSS performance mode to see if we could actually get more like a 60 FPS average here, and we are able to do that at medium settings DLSS performance. There's a small, 3 FPS difference in the 1% lows, 2 FPS difference in the averages, which, I don't think is VRAM related. It could be run-to-run variance plus the difference in the GPU coolers, but either way, it's not a significant issue. At 1440p high settings, we're seeing some small advantages for the 16 gigabyte card, but these aren't major differences, so I wouldn't say that this is like a cripplingly different experience on the 8 gigabyte card, but it does seem like the 16 gigabyte card, it's nice to have. You can see that it's reporting a VRAM allocation beyond 8 gigabytes, so it does seem to be benefiting from that. If we kick on DLSS quality on the 1440p high settings, everything seems to kind of balance back out. We're now averaging the same at 57 in the averages and 49 in the 1% lows. If we go ahead and jump ahead to testing out medium settings without DLSS, we see that they're, again, within about 1 FPS of each other, which I would more likely chalk up to run-to-run variance or differences in the cooler models than anything too significant. So it seems like at 1440p medium settings, we're averaging, in the 50 FPS range, and it's about the same on both GPUs. At 1080p resolution, we can average in the mid-50s, and it doesn't seem to be a VRAM issue for the GPUs here. Anyway, let's go ahead and look at Avatar, which, well, it did release last year. It was towards the end of last year, and it's a big visual showcase. 4K Ultra settings, neither GPU's doing well. They're at 19 FPS average, but I don't see a performance difference between the two cards. However, one is definitely reporting a lot more VRAM usage and allocation than the other is. The performance seems to be the same. This could be one of those situations where if you were able to stop and zoom in on the textures, you could possibly see different textures. Because again, at DLSS performance mode, but 4K Ultra, we're seeing big differences in reported VRAM usage, but performance numbers are staying about the same. And I did look into this engine, and it does seem to be an engine where it will just not stream in as high quality textures when it's running out of VRAM. It'll kind of adjust that automatically based on what you have. Now, I'm not really spotting those visual differences in my side-by-side footage here, but it's possible that if you got closer to some of the things in the scene that you could maybe spot more visual differences between the textures and things like that. I did turn down to high settings here, and now I'm seeing a bigger difference in the 1% lows between the two GPUs at 24 versus 19, and a couple FPS difference in the averages, but nothing crazy. At 4K high DLSS performance, we're finally averaging about 60 FPS on both GPUs. Again, only small differences in the performance numbers here. So again, if you looked carefully, maybe you could spot some differences in the kinds of textures that they're loading in. Because again, like I said, not every game struggles in performance when you run out of VRAM. Sometimes it just changes the asset quality to adjust for that difference. And I have, like I said, a feeling that's what's going on here. But again, a little hard to spot in the footage, actually. So it seems to be doing a good job of whatever it's doing to balance things out. At 1440p Ultra, we're seeing that the GPUs, again, are within 1 FPS of each other, so not too many crazy differences or anything, averaging around 40 FPS. If we go ahead and jump ahead here to 1440p high settings, they're averaging around 50. The 1% lows are a 3 FPS or 7% advantage for the 16GB card, so it seems to be helping at least a little bit here. But let's go ahead and take a look at Alan Wake 2. Alan Wake 2 at 4K high settings, even with DLSS performance mode, neither GPU is doing great, but the 8GB card is just being crushed by 35% in the averages and 41% in the 1% lows. If we go all the way down to low settings and DLSS performance mode for the 4K output, we're still seeing noticeable differences between the 8GB card and the 16GB card. With a 61 FPS average versus 49, so a 24% advantage in the averages, and the 1% lows are 45 versus 37, so a 22% advantage. So even at the lowest settings with DLSS performance, the 8GB card is still suffering a bit. And what if you want to do the path tracing mode? I didn't even try that at 4K. Went down to 1440p, went to ray tracing high with DLSS balanced, so fairly aggressive upscaling. But here, neither GPU does great, but it is better on the 16GB card by 17% in the averages and 35% in the 1% lows. But yeah, it's pretty rough on both of them. Now, if we try to kick on frame generation to smooth things out, we can see that the 16GB card is better able to take advantage of frame generation here, although you're still coming from a pretty low baseline frame rate, so it's not a great experience, but it does get your motion fluidity up to 57 FPS average and 42 in the 1% lows versus 48 and 33 respectively on the 8GB card. So again, we're seeing frame generation work better on the card with more VRAM. If we turn off the ray tracing but stay at 1440p, the differences are less dramatic, but they're definitely still there. At 1440p high settings, we see an 11% advantage for the 16 gigabyte card, and a 10% advantage in the 1% lows, but performance overall is not great. So I kicked on DLSS quality, and we're seeing a 19% advantage for the 16 gigabyte card in the averages and a 20% advantage in the 1% lows. So again, we're seeing the VRAM coming into play there as well. Even at 1080p resolution, if you try to use the ray tracing mode, even with DLSS quality, which is an internal resolution of 720p, we're seeing the 1% lows, a 17% advantage for the 16 gigabyte card. So it's looking for like these heavy-duty ray tracing experiences. Especially if you try to kick on frame generation, which I did here, the 16 gigabyte card definitely has the advantage, and 8 gigabytes really just isn't enough for heavy ray tracing workloads, even at 1080p resolution, as we're seeing here. 10% advantage in the averages, but a 27% advantage in the 1% lows when we're using DLSS quality and frame generation, along with the ray tracing maxed out at 1080p. So let's go ahead and turn off the ray tracing at 1080p, and even with ray tracing turned off, you can see an advantage for the 16 gigabyte card by 9% in the averages and in the 1% lows. Let's go ahead and take a look at another game engine. This is Resident Evil 4 Remake on the RE engine. You can see at 4K max settings, the 1% lows are the big difference. You can see massive stutters on the frame time graph, and the 1% lows are a 76% advantage for the 16 gigabyte card and a 17% advantage in the averages. But you don't have to play the game at the max settings. If you switch to the prioritize graphics preset, both GPUs are basically tied now, down to a 2% difference in the 1% lows, which is likely just run-to-run variants or cooler models. So we're seeing 50 FPS average on both of them here. So as long as you stay off the max settings, this game seems to work fine at 4K. If we go down to 1440p max settings, we're actually seeing even bigger difference here. Look, there's these massive stutters, and it's a 5 FPS in the 1% lows here, leading to a ridiculous difference in the 1% lows, even if the averages are very similar, again, when we are at the max settings. Now, if we jump to the prioritize graphics settings, both GPUs are within 1% of each other and are running great at 95 and 96 FPS average respectively, and great 1% lows at 86 and 87. So if we go ahead and jump to 1080p resolution, we can see even at 1080p resolution, the max settings are out of the question for the 8 gigabyte card, with the 1% lows, again, getting those massive frame time spikes, causing an unsteady, stuttery experience on the 8 gigabyte card, but a good, smooth experience on the 16 gigabyte card. And then we can go ahead and try out the prioritize graphics settings, where everything kind of balances out, and we're just fine on both of them, very high performance levels. Let's go ahead and take a look at Starfield. Well, Starfield doesn't seem to be too VRAM bound. Even at 4K Ultra, performance is very similar on the two GPUs. 2 FPS difference in the 1% lows, which is likely more of a run-to-run variance type of issue. However, I did try, what about frame generation? So what if we wanted to go DLSS performance mode and kick on frame generation? Well, now the 8 gigabyte card is a stuttery mess, and the 16 gigabyte card takes a 63% advantage in the averages and a 184% advantage in the 1% lows. So again, that's showing that even in games that are within an 8 gigabyte VRAM buffer, if you try using frame generation, that sometimes causes a bad experience. So if I just show 4K Ultra DLSS performance mode, you can see that there wasn't an issue. It was kicking on the frame generation that caused the massive problem. If we go down to 1440p Ultra, again, only 1 to 3 FPS differences in the averages and 1% lows, so we're performing about the same. Whereas, again, if you try to kick on DLSS quality plus frame generation, well, this time we're actually okay. So at 1440p, the frame generation does seem to work out, at least in this short test. Sometimes on a longer playthrough, VRAM can become more of a concern. But it did seem like we were able to use frame generation along with DLSS quality at 1440p, unlike at 4K resolution. 1080p Ultra, again, not a lot to talk about here. Performance is about the same. So Starfield is not heavily VRAM bound. even at 4K, unless you're trying to use frame generation, which can push it past that point. What about Cyberpunk's path tracing mode with RT Overdrive? Well, I only tested this out at 1440p resolution. And I even used DLSS performance mode just because, like, that's just the sacrifices you're going to have to make to use this path tracing mode, which is incredibly demanding. And there's not a huge difference between the two GPUs here, but there is a difference, 14% advantage in the 1% lows and a 6% advantage in the averages. So it's definitely advantageous to have more than 8 gigabytes of VRAM here. Also, if you try to kick on frame generation, we are once again seeing massive spikes in the frame time graph. So if you're trying to use, again, the big NVIDIA feature set here, including frame generation, the 8 gigabyte card has problems doing that, with massive stutters causing the 1% lows to tank to 26 FPS, whereas the 16 gigabyte card can stay at 56. So once again, frame generation causing the problems for the 8 gigabyte card. At 1080p resolution, the RT Overdrive mode using DLSS quality, so only a 720p internal resolution, it runs a lot better on the 16 gigabyte card. It's 52 versus 42 in the averages, so 24% advantage in the averages and a 29% advantage in the 1% lows at 44 versus 34. Now, also, what if you kick on frame generation? So 1080p RT Overdrive DLSS quality with frame generation enabled shows an even larger difference in the 1% lows because of, once again, frame generation uses more VRAM. So we're seeing that here where the 1% lows move to a 58% advantage for the 16 gigabyte card versus the 8 gigabyte card once we've kicked on frame generation. And again, we see spikes in the frame time graph indicating stutters on the other card. Now, not every game needs to be this demanding. So what if you're just playing esports games, right? And that's where I'll kind of end with here. So it's really your use case. I was testing these big AAA graphically demanding games, but what if you're just going to play basics, low settings, competitive settings in a competitive multiplayer title? Well, then they perform about the same. They both perform really well, and then that ends up just not really being that big of an issue, really. So what do we make out of all of this? What was the point of the video? Did we get anything out of this? Well, I would say that we definitely got something out of this. 8 gigabytes of VRAM is definitely causing problems at 4K resolution pretty much all the time, and you have to be incredibly careful what settings you use, but I don't think that's really a surprise. However, we did see it starting to cause some problems at 1440p as well. Including not being able to use things like frame generation, which is one of the big, NVIDIA feature sets here. And then even at 1080p resolution, especially when you were trying to use ray tracing and or frame generation, we were still seeing it causing issues. Now, we're always able to find graphic settings that work. So we can always turn down graphic settings and turn off frame generation to make the 8 gigabyte card run okay. But you're definitely going to have to be babysitting the VRAM, or if you're just not knowledgeable about what's happening, you might be complaining that games are stuttery, they're not running well, and things like that. Why is frame generation not working? Things like that. But when it's really definitely being caused by that lack of VRAM. So I would say that 8 gigabyte VRAM cards in 2024 are, fine if you're playing, competitive multiplayer games where you are turning down graphic settings, and so your VRAM buffer is going to be totally under control. If that's your use case, I really don't think you need to worry about it. But if you're trying to play the latest games that are, a lot of times they're designed around consoles. Consoles have 16 gigabytes of unified memory, and often 12 gigabytes of that can be dedicated to like VRAM type tasks, which means that cards that are significantly below that are going to struggle at the types of graphic settings that people, game developers are designing to run on consoles. And we're seeing that happen over and over and over again at a wide variety of settings, and even turning down settings and using DLSS and things like that. You have to be careful in order to get things to work out. So, it is what it is. If you have an 8 GB of VRAM card, you don't necessarily need to chuck it in the trash, right? You can play with it and make it work. I'm just a little bit concerned that the rumor mill has NVIDIA possibly using 8 GB again for some of its upcoming 50 series cards. And I really hope we don't see that at anything above an extreme budget level card, because we can see that games want more than 8 GB of VRAM to run at their intended settings. And you're fighting against that if you don't have it. So hopefully you guys found this video useful and or interesting. Again, if you're fed up with your 8 GB card, don't forget to check out Jawa.gg to sell it and fund your upgrade. And don't forget that I can get you $10 off your first purchase using code OWEN10. I hope all of you have an excellent day.